Good afternoon. Welcome to session 4 of this Advanced Materials Conference. Now we have a slightly different session format. So we have a discussion forum. For this forum, we have invited different speakers from different countries and with different expertise. So I would like very much to introduce the first speaker, Professor Christina Edstrom. She's a full professor at Uppsala University. She's very well known because she's leading a very strong group on batteries. She's well known all around Europe and around the world in this field, where her main scientific research interests are navigating in this complex world and very important world of battery storage. And she's also the coordinator of Battery 2030, and she's really a key person in driving Europe in this important battery-related challenge. So it's my pleasure to introduce Christina. Christina, the floor is yours.
Thank you so very much, and thank you for this invitation and a very nice meeting where materials are in the center, and materials, that's really in the center of my own research and in the big large-scale research initiative on battery materials. And I hope to show you a little bit how we are thinking in this large-scale research initiative. And of course, it can't be helped that it's also touching a little bit on my own views as a scientist. And I've been working with batteries since the 1980s. My PhD 1990 was on the sodium sulfur batteries, the beta aluminas that become large-scale storage batteries primarily in Japan. And then I moved into the lithium-ion battery research in mid-1990. And at that time, you could see pictures showing the efficiency of batteries. Sorry about the qualities from a photo I took at another meeting that was recently in Germany, comparing the efficiency with the fuel cell car and power to liquid community. And the interesting thing that the picture is very similar today that it was 20 years ago. And the difference is that the batteries have doubled, more than doubled their capacity since then, and that the materials used for fuel cells with less needs of catalyst materials and so on have improved tremendously. And I would say if the energy system is so demanding that we will probably need all these technologies, and looking at this, we can see where we need to really focus our research efforts. And I would say for all these systems, because I think they are complementary, we need to accelerate the hunt for materials. And I think this is really the importance for Battery 2030 Plus. And of course, the demand on batteries, this is a picture from European Commission and the IRCs that shows that you expect that around 2020, it's taking off, and then you expect the electromobility to really move on, and also the large-scale storage coming more and more on batteries. And the cost for lithium batteries have also decreased tremendously, expected to decrease a little bit more, though it's leveling off. And you can think that this battery, the lithium-ion battery, that got the Nobel Prize 2019, that's sort of fixed and finished and so on, but it's not at all finished. Because if you look at the need of negative materials, positive electron materials, the electrolytes, the separators, everything you have here, everything can be improved and new materials can be chosen, and it's more like a family of opportunities. And of course, the need to have enough of raw materials to feed this sector is an extremely important question. So looking at this and what Battery 2030 Plus is doing, and many of the scientists in Europe, is to look at what kind of future batteries do we see in the horizon. And you can see here that it's a whole family, and we can sort of not neglect, but research-wise, we are focusing more on the high energy density in terms of volume, the specific energy in terms of gravimetric energy, and research can move all these practical capacities shown in this plot to higher towards its theoretical value. Lithium-ion sulfur batteries have a much higher theoretical value than you can see in the practical, for instance. That's also true for the lithium oxygen battery. But if you should look at what the goal is today, that is sort of combine high volumetric energy and a really high gravimetric one, and then the solid state batteries with lithium metal or sodium batteries with sodium metal, they are the ones that are really sort of in the target at the moment. These plots are often made for the transport sector, and we are a little bit neglecting the large-scale storage. And then we have also an important group of redox flow batteries, where they also need their materials. And my vision in the future is that we should try to get them into a similar plot, and also into a plot, into a plot where we can discuss when are these battery technologies, when will we see the breakthroughs? And we think that hopefully quite soon we will see breakthroughs when it comes to lithium-ion batteries. When it comes to sodium, sodium is starting to come out on the market, and redox flow batteries. Solid-state lithium batteries are probably coming closer than we think, because it's a lot coming up now when it comes to small SMEs in this, while we have to wait a lot longer for the multivalent, at least the ones that are not zinc, and the metal air batteries. So what battery materials do we then need to think about? Well, we need to think about, are we making breakout sessions now, or what's happening? Oh, sorry, I just continue. We have to think of materials along this whole value chain and sustainability. And therefore we have the critical raw materials, how to produce materials, making larger quantities of cells without hazardous waste materials. We have to think about reducing the amount of materials, not contributing to overall energy storage. And we have to think about the energy mix in the applications to really make this sustainable. And I just picked out just to show to you how many, there's so many studies in this area, so many different attempts. You can put nano mesoporous titanium oxide. All these are titanium oxide with different structures, in different forms, in different playing around with nanotubes, mesoporous, nanoparticles, etc., with rather sometimes complex synthesis methods to do all these materials and play with them and organize them and structure them. And all these complexity has led to us thinking that we need some kind of common tool in Europe to have use all the data we produce, by cycling batteries and making different kinds of materials, and collect that and have a database and develop an artificial intelligence accelerated infrastructure for the European community. And we have this vision by using these kind of digital tools that we are developing at the moment, we should be able to have a neutral platform and work on acceleration. So this is really our vision. And our vision is to use this idea on all the different kinds of materials, lithium, sulfur, the organic and whatnot. And we think that the really key that we need to understand much more. And therefore you will find in the work program for 2022 and also more in the future, the Battery 2030 Plus topics coming out like an interface call for the whole European community to apply to. because all our knowledge about these kind of interfaces between electrodes and electrolytes, like this is representing, they are from postmortem studies. So we need much better to have data-driven models together with high throughput experiments to learn more about this. And our platform in Battery 2030 Plus that we will develop through the battery partnership in the next work program for 2022, there will be calls for this, is to have an artificial intelligence orchestrated discovery, where we are actually now building up laboratories. There is one already in operation in Münster in Germany, one is coming on in south of Stockholm, one is coming on in south of Germany, to actually screen with robotics help materials, to have a closed loop between experiments and modeling in a way we haven't had before. So this is sort of the vision that we're working on. And I can tell you it's a lot of work if you want to make databases that are open and where you can find trace your data sets and make them sort of reusable, all which applies to the FAIR principle. So by this, I just want to say that we have a roadmap where you can follow what we want to do in the short term, medium term, and long term, because the vision from the beginning when we built this idea was that it should be at least a 10-year sort of development of these ideas. And have this synthesis and so characterization hand in hand with the modeling. And we also think, because Battery 2030 Plus is a little bit wider, that we see that we need also to work in the societal aspects, social acceptance, trust in the technology. And we do think a lot about skills, because skills is coming up as one of the key issues for Europe if we are really to become a continent where we produce battery cells, which it looks like, and transfer the society to an electrified society. Skills, upskilling, reskilling, and of course lots of young people in this field, that will be very, very important, just as trust in technology, safety, life of batteries, and in this as well. But all the core in this, that is the materials. So we are spread all over Europe, 24 countries. Portugal is there too. And we have the large-scale facilities on board helping us with this. And I thank you for letting me speak about my favorite topic, materials in batteries.
Thank you very much, Christina, for this really very, very interesting presentation. I would like to know if there is any question or comment, although we have some time for discussion at the end of the session. We can open the floor here for a short question, but I remember that we have the roundtable discussion afterwards. So, yep, no, so we'll keep the questions to the end. Thank you very much, Christina. And now it's my great pleasure to introduce the second speaker, Professor Marko Topic from the University of Ljubljana. She is the chairman of the European Technology and Innovation Platform for Photovoltaics. So it's my pleasure to introduce you, and the floor is yours, please.
Thank you very much. I hope you can hear me and that you can see my screen with the slides.
Yes, yes.
Okay, thank you. Dear ladies and gentlemen, a warm greeting from Ljubljana, Slovenia. I would like to thank first the organizers for inviting me to speak about the progress of advanced materials in photovoltaics on behalf of European Technology and Innovation Platform Photovoltaics. I'm sure that you know the concept of European technology and innovation platforms like Battery 2030 Plus. ETPV is embedded within the Euro Energy Union and SET plan, and it provides advice, produces reports, position papers, and holds workshops and conferences on solar PV related topics. I'm sure that at least you heard for the tremendous development that photovoltaic technology and materials have seen, especially during the last decade, both in the laboratories and on the markets. In 2018, we started to prepare the vision how solar PV can help in reaching the 1.5-degree climate target. And the European Commission actually is setting the right policy framework to make it happen in line with the Green Deal and Recovery and Resilience Facility, and of course also in the frame of United Nations Sustainable Development Goals. I invite you to have a look at the recordings of our annual PV conferences that at least in the latest one a month ago, actually we unleashed how solar PV is enabling to reach by 2030 the 55% reduction of greenhouse gas emissions. The conference conclusions were actually that Europe should move from lab to fab and from fab to field to strengthen the whole value chain and seize the fair share in global manufacturing for the sake of resilience and sovereignty. We need to do a lot, and definitely we need to do it fast. For more than a year, we have been focusing on strategic research and innovation agenda for photovoltaics, bringing up many experts and putting together the opportunities for European solar PV in two time frames, till 2025 and till 2030. The opportunities are identified in 5 challenges, as shown, with detailed roadmaps and KPIs that are currently in the phase of public consultation. And of course, we will share the information, complete full information in the near future. But so the clean energy transition is just getting started, and we envision a world with 100% renewable energy sources supply, where electricity is accessible to all, and where electricity markets make major inroads into satisfying final energy needs for living, including both communications, transport, efficient heating, and even synthetic fuels, using the power to X option. So if I focus now on advanced materials and where we are heading to in research, development, in innovation, I would like to use our, let's say, figure of merit, which is the conversion efficiency, as shown here in the evolution of the last 5 decades, primarily focusing on the last, let's say, decade or 8 years, where there is a technology that demonstrated the fastest growing conversion efficiency based, and this is on the single junction as well as in the tandem cells, reaching or exceeding 29% conversion efficiency based on perovskite semiconductor materials. The perovskite absorbers exhibit unique properties with a crystal structure of ABX3, constituents part for the position A, for the position B and X, which give us a tunable direct semiconductor with a band gap from 1.2 electron volt to 2.3 electron volt, directly fitted for the use in photovoltaics, exhibiting high optoelectronic quality, and this makes this material not only suitable for solar cells, but also in other optoelectronic devices, as well as other detectors. So perovskite solar cells are a thin film technology made of polycrystalline absorber film with low defect density, with a variety of deposition techniques, even on a large area, like slot die and blade coating, and of course also suitable for tandem integration for the ultra high efficiency solar cells, either in combination with silicon, with thin film CIGS, or perovskite tandem architectures. Perovskite tandem solar cells really offer high efficiency conversion efficiency, applying optical optimization as well as electrical optimization. Let's say in the last year, monolayers, we could say even as a 2D semiconductor materials are introduced for passivation, resulting in even higher open circuit voltage and excellent energetic band gap alignment for even more efficient charge extraction. This is an example of the certified conversion efficiency exceeding 29%, the first of the kind, exceeding 29%, applying 4 packs, so there is a huge unexplored area of new advanced materials towards ultra high efficiency of solar cells. And efficiency is not the only aspect that we need to focus on. It is, of course, we want to make it scalable, upscalable, and of course, we want to make it stable. In terms of stability, of course, we deal with organic-based materials or hybrid concepts, inorganic, organic materials that are somehow water vapor sensitive. We have to deal with field testing, so we have to move from lab to the field, and we have to take care of excellent encapsulation and compactness of all the multi-layer structures. In terms of scalability, definitely we need to go to the wafer size solar cells, as well as to the large area, even few square meter size areas of deposition or roll-to-roll process with endless roll with achieving high production yield. And of course, it is always a trade-off between excellent and record solar cell efficiencies, and then production average of conversion efficiency. We need to further standardize the testing protocols. This is an example where the PV community has already reached a consensus, and this is published in the paper in Nature Energy journal. And definitely we need to do not only laboratory stability testing, but also outdoor testing. And of course, we need additional equipment to explore where the losses are in the tandem structures and tandem cells to make it even faster, the progress. So it's a complexity and an interplay starting with advanced materials, focusing on efficiency, but definitely also with the second and third pillar about stability and scalability. And perovskite solar cells are making a way toward the market based on the material optimization loop. And coming to the very hot topic, scientific field, perovskite solar cells. This is a graph where we can see how fast the number of publications rises with more than 16,000 papers, with more than 4,000 papers last year. Of course, this is not possible for each individual to cope with, but PV community has been organized. We have volunteers, both PhD students, postdocs, and other researchers working in the field. See the cooperation, direct benefit of cooperation to collect the all published data in one database. And I'm happy that this has been also implemented in the one of the Israeli startups who helped bringing up the vision to the living platform with a database. Each single point in this graph, which shows the dependency on the band gap and conversion efficiency, is linked to a paper. So you can actually click on the dot and you immediately see what is the paper published in peer-reviewed journals. With that, I would like to end that definitely solar PV is entering a terawatt era, and this is just the beginning. International Energy Agency recently declared solar PV as the king of the world's electricity markets, and PV, ETIP PV adds that PV offers unique opportunities for European energy transition, quality jobs, as well as technological and energy independency. Thank you very much.
Thank you very much for your presentation and for this comprehensive view of PV over our next future. We have a time for one or two questions. So Professor Marco Topic will be very happy to answer your questions, please. Any questions?
I have one question, then if you allow me, Fatima.
Yes, please.
Yes, so thanks for the overview. I have seen that you have focused on the on certain type of solar systems. I'd like to know whether it's just because it was illustrative, or is it because that's the trend for the technology?
Well, thank you for the question. Actually, it's an example how advanced materials can make really fantastic progress. I'm blown away by the progress that perovskite photovoltaics has made so far. It's less than a decade. It is well known that about 95% of the market is mastered by silicon technology, which is of course also a high-end technology. It's not just a simple silicon wafer-based solar cells, but there is a lot of material research there as well, not only in the absorbers, but much more is focusing on the concept of selective contacts. Since we have to deal with the photogenerated carriers, both free electrons as well as holes, and the selective contacts are those magic words to make this architecture up to the perfection, so that we extract everything what solar energy offers. And the tandem concepts are as well, say, high efficiency architectures that are driving the research and innovation for further for strengthening competitiveness as the technology to make electricity.
Okay, thank you.
Okay, thank you very much. I just realized that the next speaker is not present. So Professor Deborah Jones is not present. This means that we have here a small period that we can use for further discussion. So maybe Christina, you are still around. So I kindly ask the participants to put a couple of questions to Christina and to Marco, and we can use this 10 minutes break to discuss these two previous presentations. So your questions are welcome.
So if you allow me again, Fatima, then I will have questions
Go
to
ahead.
Professor Christina. Thanks for the overview that you gave on batteries. It's always good to see what the academics are doing in the field. So very interesting. I would like to ask you whether, because you seem to have quite a lot of years of experience, are you doing those developments with companies, with the private sector? Or is there a trend to, for those developments that are more related to SMEs? How do you see the field of batteries that you are working on?
I think this landscape where we are changing now to have more gigafactories in Europe. Some of them are, of course, Asians moving into Europe, but we have also some of our own. I can see, especially in my own country, where we have Norfolk establishing themselves, that it generates a lot of extra activities. It generates the formation of small SMEs. And of course, it's a question whether they can survive or not. Sweden has an funding innovation system, which is maybe a bit special for Sweden, I don't know, but almost all industrial research we're doing with companies from university side is funded by public funding. It means that the industry comes in and they can get a little slot of money, but they have to also give their in-kind support to this. And so the funding goes more or less to the university. So we can do research that perhaps is not really possible or too time-consuming and too costly for the companies to do, but we do it in collaboration. So we have recently formed a Swedish battery center called BASE, where we really work with a number of companies, and it's a mixture of SMEs and big ones like the automotive companies, Norfolk, ABB, etc. That's one way of organizing it. To have direct funding from a company that paying a PhD student for you in my country is very unusual. They tend to go through this public funding streams. And that differs in the different member states. But I see a lot more coming up because, you know, solar cells and hydrogen society, they have, from a European perspective, have much larger funding at the European level than batteries, because you thought that this is a box that always worked and it's just to buy it and put it into application. And quite recently, the transport sector have realized that they need to open the box and look inside and learn more about it to actually be good customers, to put pressure on the cell producers. And I think this has started a lot of new activities and new ideas, especially on the material side. Also,
Yes.
I can see that the graphene flagship has also generated new companies that are coming into the battery field. So it's an interesting development.
And do you see the raw materials for battery? I mean, is it something that is of concern, or is it a topic, or is it not a topic? I mean, because we read different things about it, so I'm not sure where the truth is, but at least from our side now, we get investors who are interested in this area. And we see clearly a sort of monopoly for some of the raw materials, and we understand that Europe wants to go a bit away from that monopoly, which is understandable. So are those, because that leads also to a lot of effort in developing new materials to avoid looking at those monopoly type of raw materials. Is it something that you work on, or is it a problem?
It's almost the first question. What raw materials can we use? Can we really make good batteries without cobalt, for instance? Can we use more of biomaterials in batteries, or what you say, renewable materials in batteries? And in some sectors, and there's separators, new cellulose type of materials are coming in. We have also more biocarbon materials tested and coming in. So yes, it's a very big concern. And I think that's why I should motivate that better. When I put this slide with all these kinds of different possibilities of battery chemistries, I think there is not one battery that can solve all problems. And the reason is really the raw materials. We might need to differentiate that we have some chemistries for large-scale storage, some other ones for the transport sector. And I think the winner for the transport sector, because you can make them compact and small, will be lithium-based batteries.
But that means that the investments will go into those type of alternative materials. That's an important movement of...
But we have new battery regulation coming in, and this battery regulation can actually put some limitations on what we really can do, because it's so much focused on us doing a lot of recycling. But if we do as scientists coming up with an idea which is sort of making it less profitable to recycle, then we are we building into too much economy into these systems? It's an interesting and very political and difficult question to handle, actually. What the battery regulation says, though, is that you as a scientist, you're allowed to study whatever you wish. So it's not limiting research in that sense. But the funding streams can limit you and push you into one direction.
Okay, thank you very much for this very nice discussion. Thank you, Fuzia. Thank you, Christina and Marcus. So we can move. Please, we'll keep discussing at the end, but we can move to the next speaker. João Calado is a senior consultant. He works on the technology development at Bondalti, a Portuguese company related to the chemical industry. João,
yes,
thank you very much.
Good afternoon. It's a great pleasure to Bondalti to be invited to share a little bit the vision of the industry, the chemical industry in this world. And for me particularly, is a great honor to be presenting that. Okay, a little bit about, Bondalti, a little bit just introducing the company. Bondalti is part of the, first of all, Bondalti belongs to José de Mel Group, one of the Portuguese largest conglomerates that operate in several sectors. Bondalti is the branch that is in the area of industrial chemicals and water treatment systems, and there are a few others branches like infrastructures and road, private hospitals and clinics, and several others. But today we will be focused about chemical industry. So Bondalti is a manufacturer of industrial chemical with units to produce in Portugal and also in Spain. It's the largest producer of chlorine in the Iberian Peninsula. It's one of the world's top non-integrated manufacturers of aniline and supplying a vast array of clients in Portuguese and international markets, from Australia to China to everywhere. Since 2020, it's also present in the water treatment system market, and is strategically committed to the segments in which it operates, with always innovation, expertise, and human development about that. In terms of two areas, there are two different areas where we operate. One is what we call aniline and organic derivatives, one side, classic organic chemistry, also chloroalkali, and in another side, water treatment systems. So two main areas of activities in the business. Bondalti, today's, so not only for the future, but today's the product applications already play a key role to sustainable goals. As an example, we have the production of polyurethanes that are fabricated with aniline, which have are very important in thermal insulation materials for construction and cold appliance. So to reach the building energy efficiency, that it's a great goal from EU. Also, another example of materials, we are in a conference of materials like aramid fibers that are used from car tires to air freight containers, and also protective clothing, which allow to make them stronger, lighter, and more durable, with a long cycle life between being recycled. Pharmacology, all what has been happening to all of us, so it's also important. Paracetamol is used to treat several common diseases like hernias, muscle hernias, arthritis, and several things that are important to keep alive. In terms not of organics, but in the chloroalkali business, the main applications, which are sometimes a little bit counterintuitive, but we have PVC, aluminum metal, polyester for wind turbine blades, soaps, cellulose pulp, disinfectants, so much important in this last year, biocides, hydrogen production, and which we probably are not aware, but the modern medicines, at least 88% of which rely, at least in one step of preparation, on chloroalkali chemistry. So important. Water treatment, water is not, I think we realize the importance, at least we are 70% of water in our bodies. So it's also a very important area with several techniques to treat water to allow to be recovered, to all of these, to water consumption, water recycling, salination, and also several things that are critical for all our lives. But from time to time, change appears. Not only change as we have been discussing, also in geopolitics, in the arts, in a lot of areas, but of course, also in the chemical industry, and it's a challenge. The carbon neutrality goals, green chemistry, circular economy, fossil fuel replacement. Also, investors leaving unsustainable assets, which is a very important driving force to change the things. Energy production, energy storage, chemical recycling, hydrogen economy, and electrical mobility. But change is, things are changing, as Bob Dylan used to say, but change is also a fuel of life. So it's also a source of opportunities. And Bondalti is firmly determined to comply and have put to itself a goal to 2030, with firmly committed to determine to reach a decarbonization of its own process, its own internal process, and along the value chain also, but also entering in a new generation of products that enable a more sustainable products for all the society. So this is seriously taken by our board and all the company in order to transform, and wants to contribute to the long-term strategy defined by European Commission for an economy with neutral impact on the climate. where to look? Three main vectors. Electrolysis is because you'll see. Also cellulose and biomass, and photosynthesis, that probably more than 3.5 billion of years ago, life was able to find out an incredible material, a manganese complex material that was able to split the water in hydrogen and oxygen, and all of we are aware of how is it important, this combination of materials and chemistry. These areas, our internal developments, of course, are supported on the strengths of the company. So Bondalti has experience, namely nitration reaction, hydrogenation, membrane electrolysis, energy management, material synthesis, and water treatment. And so the three main areas where we are looking for these opportunities are on electrolysis, one, because it's very, very good to green hydrogen and ammonia production for one side, but also for the lithium processing unit. And the reason is that both can potentially be based on electrochemical process, where Bondalti already has large experience in its current chemical plants in Portugal and Spain. I just quickly share, we were discussing last week with a legendary man that was the founder of the adiabatic nitration. Is now more than 80 years. And we were commenting to him, oh, now you are still studying a new electrolysis. And he said, one electrolysis? No, more than 10. So this trend that the previous speakers has spoken about, the trend to electrify everything, is also reaching the chemical industry with the assumption that the energy is renewable. What happens is that even if the thermodynamics doesn't favor the reactions, but with energy, electrical energy, electrolysis, it's possible. So this is changing again the game. And the other one that, of course, it's related with biomass. As you know, biomass is very important, has been used for burning and producing energy. What is a trend that we now see is that is becoming now the opportunity to develop new ways to use the raw materials, the benzenes, all of a series of compounds that can be used instead of fossil fuels. As just to sum up, we feel that chemical engineering departments in all the world basically now are trying to overcome and to enter in this challenge with two main areas, probably resume to two: energy and materials. And it's what we feel and that's it. Just to share how a classical chemical business are we being challenged, but entering in these new opportunities with all the enthusiasm. Thank you very much.
Thank you very much, João. It's really nice to see that our core traditional chemical industry has really the eyes on the horizon.
Yes.
But beyond the present moment, it's great to see these really the industry, the strong chemical industry, looking into these challenges. Well, we have a couple of minutes. So I kindly invite the assistants to discuss, to present some questions to João, because we still have 5 minutes before the next speaker. Are there questions? Please. We have a lot of attendance, 119. So I guess there will be some questions in your minds.
To ask questions again, Fatima.
Please, Fuzi, go ahead.
Yeah, thanks for your overview. I have to confess, I didn't know your company. So
now you know. Now you know.
I know. And you know, I am based in Qatar, so obviously chemicals and water treatment is extremely important.
Mm-hmm.
So my first question is whether you have any market in the region or not.
Yes, yes.
Okay. I was not aware of it yet. I was curious.
Mm-hmm. Then we can share the contacts and put the people in charge of that. But yes, we have already presence in that area.
Okay, very good. And a sort of technical question. While you were talking, I was looking on the net. You have a project on hydrogen that has just started. Can you tell us a bit about it?
For the moment, it's an area because in our process we already produce hydrogen, you know, in the electrolysis, and we use hydrogen to make the hydrogenation of aniline. So this is for us, it's something. Even in the past, even in the 60s of the past century, we used to make electrolysis of water that now is coming back, but with a very electricity from the renewable from the dams, from the water, you know. It was very cheap in Portugal, and it works perfectly during a few years. So it's interesting that life has these cycles. We have still an old part of that plant from the 50s and 60s that now is coming back to the electrolysis of water. As okay, photosynthesis were very efficient 3.5 billion years ago, but now we are coming back on, of course, on the assumption that the electricity is renewable. In Portugal, we are not bad because if I'm not wrong, we are not quite far from 60% of our supply. Yes. And and because we are a big consumption of energy, I think almost 1% of in Portugal, you are able also to use the more production during night when the renewables can be optimized, and this type of managing energy. So it's a quite important topic for us.
So you would be, your position in the market would be as a producer of hydrogen? This is your position?
Generally hydrogen, and we also use ammonia, so that's the reason why ammonia also appears. So in first, what is in our minds is as an auto producer. This is important. Then in the long term we'll see, but it's something that we are able, we touch, we know how to. Okay, we have experience in managing hydrogen, safety of hydrogen, this type of things that are important in the practical point of view.
Clear.
Okay, thank you. Thank you very much, João. Thank you very much, Suzy, for this nice discussion. We can continue at the end of the session for the roundtable. And now it's my pleasure to introduce our next speaker. Professor Constantine Galiotis is coming from Athens. Is a full professor at University of Athens, and he has an outstanding CV, and his main research interests, if I am correct, are focused on the area of graphene and composite materials, correct? So Professor Galiotis.
Yes, thank you, Fatima. Indeed, I was born in Athens, but the university is in Patras, which is 200 kilometers going west.
My apologies.
No problem, no problem. Athens is in my heart, and some of you may remember that I organized in 2014 the Industrial Technologies Conference as part of the Greek presidency. And that was in Athens, and materials, of course, were represented there quite highly in that particular conference. So let me share my screen, if I can. Do you see my screen?
Yes.
Okay. Just 1 second. I need to find the pointer. never mind. You see the pointer here?
Yes.
Okay, so today I will give you, let's say, a few introductory notes on functional composites and why these are important for the new challenge that we face going to green and sustainable Europe. At the end, I will say a few words on the work we're doing currently at the University of Patras, and also fourth is a network of institutes all over Greece. So we have one on chemical engineering in Patras. So I'm wearing two hats, one the university hat and the other is the researcher hat. So you will see my two emails here. Okay, now first of all, let's define what we mean by functional composites. I think nowadays we're moving away from monolithic materials. As you all know, we're trying to combine materials and by combining to in fact achieve new functions and improve the current state of materials properties. For instance, we can go to low weight and mechanical enhancement by adding the right ingredients, or have magnetic behavior, electrical behavior, optical properties are also important. Environmental properties, also a resistance to corrosion. For instance, I will say a few words about that later. Coatings are also important. Coatings can also be composites. And of course, in some cases, high temperature resistance is important as well. So in other words, we're combining functions, we're combining materials according to our needs. It's what, in fact, this morning was mentioned as tailor-made materials for our needs. And so it's a whole world that's opening up in this area. And of course, the markets are driving this. For instance, look at aerospace. Aerospace, already they're using high-performance composites. For many years, we're flying on carbon fiber composites. This is over 80% by volume, but still there are challenges. New manufacturing processes are needed in our space to drive costs down, to enhance automation and speed of processing. And of course, quite important is recyclability. You may have seen cemeteries of airplanes in Texas and other US deserts, and that blows your mind. There are square kilometers full of airplanes sitting idle at the end of their lives. I think we should try do our best to recycle these monsters, these really very, very big composite structures. When we move to automotive, okay, the challenge is to go fully electrical on passenger vehicles. How can you do that if you don't reduce the weight of a car? It would have been impossible. So lightweightness here is a challenge, and still we haven't reached the under ton type of weight for a car, for a passenger car. To in fact, otherwise you would need really, as we do today, huge batteries to drive these electrical vehicles. And that reduces, of course, the range of a car. For civil infrastructures, okay, this is an area where high temperature is really polluting the environment. So we have to go to lightweight, high strength structures, but at low temperature processes in order to drive down CO2. And for fuel cells and batteries, we heard earlier, innovative non-metallic materials that operate at high temperatures of high efficiency are needed, in fact, in order to have a more efficient fuel cell and batteries type of assemblies. In oil and industry, durability is important. Heavy structures offshore have to be durable in order to, in fact, and sustainable as well. Otherwise, we'll have to every now and then build new structures all the time. And of course, I'm actually using this cycle by going to renewable energy and in particular wind energy. There also have the very, very, very large structures made out, the blades made out of composites. And again, these are thermoset made out of thermoset matrices, which are difficult or impossible to recycle. So again, recyclability is a great challenge. So we need, in all these cases where we have composites, traditional composites, we need to make progress and make progress towards green Europe, green energy and sustainable future. And the market still is quite healthy in this field. We have, let's say, over 40 billion the functional composites in this year, by the end of this year. And of course, Europe has a very healthy annual growth in this area, currently at about 17 billion, and is growing till 2025 at a rate of 7.5%. And again, these are the traditional carbon fiber and glass fiber composites, but other little things here are expanding. And what are these other is, of course, the use of nano materials and nanotechnology, which is yet another sort of ingredient that we can add. And we have plenty of possibilities here. We have inorganic nanomaterials, like the metal chalcogenides. We have organic nanomaterials, which are different molecular structures, polymeric in particular. And of course, as you heard earlier by many speakers, we have graphene, fullerenes, carbon nanotubes, carbon dots, and more recently, mexins, carbides, that of course, we can add new properties and functions, have multifunctional materials, quite complex multifunctional materials that can do a lot of functions. For instance, here in the automotive, they can have an effect on paintings, catalysts, tires, sensors. In heavy engineering, wear and tear can be enhanced, lubrication, sliding of parts with graphene. That has been proven an interesting area of development. And in construction, thermal insulation, flame retardancy is also quite important, and even in the electronic industry, where you have displays and filters and anti-static coatings, nanotechnology plays a part. And having said that, I mean, this introductory work, I would say a few words, not too technical, on what we're doing in my group. So, and how would this ties in what I said earlier. So we have three areas: fiber reinforced composites, FRC, polymetrics composites. Okay, some fiber reinforced can be also have a polymetrics, but this particular thing will be just polymer with other additives and metal matrix composites. I'll just show you a few examples in the limited time I have. So for fiber reinforced composites, what are the current advantages in conventional fiber reinforced composites, which I've mentioned earlier? High strength and stiffness, corrosion and moisture resistance, new manufacturing processes, which are already coming in. But there are other things which are important. These materials are quite brittle. So fracture toughness is an important addition. And we will show how fracture toughness can be enhanced with graphene-related materials. Graphene-related materials can be any material that has graphene, which is less than 10 layers, not graphitic, but graphene-related, and damping enhancement with the same type of particles, which are close to the to monolayer graphene. I'll show you a few examples of that. So starting with where we are. So if we use an Auschwitz diagram, Young's modulus and tensile strength, which is important to place ourselves in terms of mechanical properties, here are carbon fibers, quite high up in modulus and strength. And these are glass fiber composites, much less in modulus and strength. And graphene are up here. So we're moving this part into that. And of course, then we have achieved new functionalities. That's what I'm trying to say. For instance, let's look at fracture toughness using a carbon fiber composite to which we have added in the matrix graphene or graphene-related particles. And this is a typical sort of experiment of the so-called mode 1, the progression of a crack as you open up the structure. And these are different type of curves you get. What you see quite clearly is a initial fall of crack propagation. And you will see which corresponds to a quite heavy increase of GSC, of the fracture toughness, from 300 joules per square meter to 600 for very, very small percentages of graphene-related material, only 0.5% by weight. I think this is an important finding because you don't need, and of course also reflects on cost, you don't need really too much of that material to enhance the fracture toughness. And what happens is that a crack that tries to propagate within the material comes across a graphene layer and then it deflects. And that of course consumes energy. And this improvement is quite important, you will see here. But if you carry on, and this is what we found in many cases, and you increase the content, because of agglomeration, you lose this profit, this gain, so to speak. So less the better, and it's of course less expensive. And the same is also thing for is the same thing we have discovered when we look at damping characteristics. It's another problem with this brittle and stiff lightweight structure with carbon fiber composites. The damping is not very good. And we looked at, we have some tailor-made experiments on the vibration properties of these structures. And you will see with small percentage of graphene, the whole amplitude versus time curves are affected quite considerably. And here you will see the pristine damping at carbon fiber, the material. You will see that the carbon fiber is much less than the knit resin. So when you build a carbon fiber, then the damping becomes much worse. You add 0.15% of graphene and it shoots up quite considerably. Then it starts falling down again. And the yellow and the green curves are the interface areas. So the interface area where you have a high interface area which enhances the damping is still small at 0.15%. When you keep on increasing, it doesn't necessarily a linear increase the damping, the zeta parameter, the damping characteristics. Again, the reason for that is when you have highly dispersed graphene or graphene attached to the carbon fiber surface, all these structures will be highly dispersed, or the friction of graphene with the carbon fiber itself, all these are helping to increase the damping of the structure. But if you go to very high percentages, then you will see you lose this. So again, low percentages are much better. And this is exactly what we are discovering. For fiber reinforced composites, we have in the graphene flagship, in which I lead the composites work, we look at, I don't want to, because these are still not published work, we look at different parts of a car. As in some cases, we improve the fracture toughness. In other cases, the damping characteristics. You don't want to drive a sports car in Portugal, an open air car like that is shaking a lot, like a Formula 1 car. So obviously, we have to work on the damping and noise propagation characteristics in this type of cars. And this is, of course, a collaboration with Dallara Italian sports car manufacturer, and this is a Stradale type of sports car. And we're using this because these cars are made almost 100% by carbon fiber structures, at least the exterior of the car. And this is what it will be coming, in fact, to us in future. All passenger cars will be made. As I said, this is it is a need to go for lightweight cars, and all these experimental or sports cars are the pioneering structures, and the passenger cars will follow suit.
Professor Galiotis, we are running out of time.
Yeah, I'm finishing off.
Thank you, thank you.
So we have the Polymetrics Composites here. I'll show you the work we do, which is making master batches. So this is a collaboration with another flagship partner. We're making master batches that incorporate polymer and graphene flakes, and they have it's easier to process and have they add and enhance nylon with thermal conductivity, increase of impact resistance, barrier properties, and more importantly, the fire resistance, fire retardancy, where you try to burn a polymeric handle. As you will see here, it doesn't burn. It forms a protective char, and this is a composite with and without a graphene in the matrix, as you will see how much it behaves, and it doesn't burn fully. And the final thing is, which is the metal matrix composites, which I promised at the beginning. And here we'll look at the corrosion resistance who can cover the metallic structures with either electroplating, deep coating, or spin coating. And of course, we have different thicknesses of graphene layers and coatings on these metal plates. And we will see that the corrosion resistance moves to the potential to positive values. The corrosion is much better resistance. And here is an example, which I will play very briefly. And you will see this is a steel wire into hydrochloric acid. And of course, it completely dissolves the wire into the acid. And you will see the black is the same wire, steel wire, covered with graphene, and nothing happens to it after hours in concentrated hydrochloric acid. And this is just to thank my group and my funding sponsors and all of you for your attention. Thank you.
Thank you very much, Professor Galiotis, for this comprehensive view of this important area of material in material science. So I think we can keep the discussion for the roundtable. And now I pass the word to Dr. Fouzia Anour. Dr. Anour, she works for the Qatar Free Zone Authority, and she is Director for Strategy, Sustainability and Industrials, and she has over 20 years experience in the industry, mainly related to aluminium and steel for the transportation sector, automotive and aerospace. Fouzia, the floor is yours. Thank you.
Let me try to share the screen.
Yes, you can share.
I can share, okay.
Yes.
How do I do that?
You have a green button,
yes, I did.
Share screen, and in the next screen, you need to choose where you want to share.
Yes, so it's not working. Okay, my presentation is open, but...
Okay, and when you click on share screen, you have another window with...
oh, yes, that's it.
Yes, yes.
Thank you.
Perfect. You can put on the full screen and it's working.
Yes, let me try to put it on the full screen.
Yes.
Can you see it now?
Yes, yes.
Okay. Okay, great. Okay. Thank you very much, Fatima, for the introduction, and thank you for inviting me to this panel. So I will take a more macroscopic view rather than a microscopic view on the subject, looking at a high level and focusing on, in fact, materials or advanced materials investments, what is happening globally, how it is affecting, how certain elements like sustainability are affecting the sector. And I will, at the end, just give few words about what we are doing in Qatar for that. But let's start from the beginning. I mean, advanced materials, they are very strong catalysts for economic development. I mean, big economies like the one of the US, believe it or not, they started their development with the petrochemical industry, so materials. And there is a very simple reason for that. It's because advanced materials are the center of all industries. So whether you speak about packaging, about energy for generation of energy, of storage, or you speak about electronics, about construction or health, or transportation, all the industries have materials as the basis. And the competitiveness is a driving force for all of them, and that leads to a large spillover effect. So what I mean with spillover effect is that whatever you develop for certain industries will have a lot of links with other industries. So that means that if you start by having the petrochemical industry, for example, then you will start to have the transportation, you will start to have the automotive, you will start to have other industries that will be basically hooked to them. So for economic development, advanced materials is a very strong catalyst. And if you look at the numbers, globally, it's a huge market. It is expected to reach nearly $2 trillion by 2024, with the growth rate around 5% of CAGR, which is big. In this slide, you see all the different industries that have a link to advanced materials, right? So here you can see that, for example, all the new applications like autonomous vehicles or advanced robotics, even the batteries, we heard this, a presentation earlier, they have a huge industrial growth, right? If you think of the mobile and internet, there is also, those have a huge growth, around 20%. But all those are linked to the development of the advanced materials sector. So that means that basically the driving force for all the applications, that's advanced materials, and we see a lot of changes in those. What is also very important to notice is that the region that is going to drive all the demands are going to be in Asia Pacific. I mean, all the demands, I mean the largest amount of demands, it's around 60%. So that means that all the changes, whether they are on sustainability, whether they are on customer experience, that will be driven also by that market. Now, if we look a bit deeper in terms of investments, where the money goes, because that's very important to understand where the money goes. It's around 3.5 billion that was invested during the period of 2018-2020. Those are the latest number that I got. So it's huge. And if you look at how it is dispatched, the number one, which takes third of the total investment, is nanostructures, nanomaterials. And if you look by geography, this is why it's very important. I thought that is a very relevant information for the conference today. US is by far the largest source of investment for advanced materials with 2.3 billion. And second is Europe, so which is good. That means that Europe, of course, is driving the trends, but you have next to Europe is Singapore. I mean, Singapore is extremely small, And it puts as much money as Europe, investing as much money as Europe in businesses. And it's quite focused, I have to say, rather than Europe. I mean, I didn't show it in this graph. It's a bit more dispatched among different applications, but Singapore, it's very focused on certain industries that they believe will contribute to the economic development. And of course, Japan is a big one. So there is a bit of differences in geographies, but the big trend and the amount is quite big for advanced materials. So another factor that plays a big role, of course, is all the mega trends. So advanced materials are, in fact, the response of the big mega trends. We have heard about it all today. And they are also an integrated part of all the business, large corporate business strategies that are also driving the business. So I'm sure you have heard about Total that has just changed their names into, I need to change the logo because now they are called Total Energies. So that includes hydrogen, that includes biomass and all type of clean energies. And you have also all type of materials that have been developed also as a response, like the bioderived materials for health application or anything that is related to recirculation, or let's say the circular economy. But what is important to notice here is that, again, in terms of investments, the large materials corporate companies, Total is one of them, you have also BASF, you have Arcelor that just has announced not so long ago that, like 2 or 3 days ago, they have announced that they will have their own investment fund. So they all have created corporate venture arms. And the main reason is that there is so much changes in the materials field that for their own, let's say, growth and sustainability as a company, they need also to have a good grip on what are the latest innovations that are happening. So that's the first aspect. So basically, it's a big area. There is a lot of investments. It represents around $2 trillion of market, which is big. And there is a huge change that is driven by sustainability. That is very clear. Now, we all know that for advanced materials, the innovation is not like in some other sectors, right? You need, there is a long journey for the TRL levels to move from experimental to basically to the large scale. And that is specific, in fact, to advanced materials. So there is a bit of, let's say, limitation because the development times are very long. So if you think of an existing material for a non-critical component where you just do a bit of a tweak, it takes 2-3 years to come to the market. And then if you think of a completely new class of material, it can take up to 20 years. Or a new material within the system. So for example, for cars, it's basically an average up to 10 years. So any that I had learned, any material that you develop today, that you start with an idea today, will be in a car in 10 years, not earlier than that. So that requires a lot of efforts to minimize, in fact, the cost of the materials development, also because it's extremely CapEx intensive, and because the time of commercialization is large, it requires a lot of alliances and partnerships to share the risk and also maximize the outcome. So therefore, if you think of it as a vector for economic development, this is how we look at it in that way in Qatar. So that means that we need to have sort of alliances and partnerships with companies or with institutions to tackle those materials development. So hydrogen is one of the examples. Solar is also another example, but it's valid for any type of material. So In the case of Qatar, we have used materials as the vector for the development. And we have a free zone where we welcome all the investments from outside. And we have also what we call a Doha Venture Fund that is meant for those technologies. So clean tech is one of them, is one of the focus of Qatar. So this is not an exhaustive list, it's just a bit of examples where the focus is. You know that Qatar is a gas producer. So obviously energy is a sector that is known. So looking at energy storage, energy extraction or generation and consumption, finding ways to optimize that, this is something that of course we are looking at, and we welcome investors, and we invest in ourselves also in companies that are in that sector. The same for construction. Construction, as a developing country, construction is always a big sector, and there is a lot of development, you know, linked to sustainability. I could find one Portuguese company, an SME, that seems to have a very good product related to absorbing bricks to reduce carbon and pollution. But you have also all those nano coatings or self-healing concretes that are coming to the market. And of course, as one of the market for material that is important for the region is the sport industry. So there is a lot also going on there, with a lot on recycling, sustainability, and using 4.0 industry, and using sport and smart materials for sportwear. So basically, what we are trying to do is to leverage all the new developments, invest in those developments, and get companies to come and offer the possibility for them to grow as well in a market which is very large, which, as I mentioned, 60% of the demand is going to come from Asia in the coming decades, at least. So this is in brief really the message I wanted to give. I know that I'm the last one in the program, so I didn't want to keep too much of the time of the people. So I tried just to give a bit of an idea of what it's all about, and give a sort of a different perspective to investments in advanced materials.
Thank you very much, Fuzia, for this very important message about the impact of advancing materials for economic development, because we clearly see from your presentation how important is this topic for boosting the industry competitiveness. So we are just on time to go to the roundtable, so if you can keep on the screen, I just kindly ask you please to remove your presentation. And now I would like to call back to the discussion. So Fuzia is already here. Christina, I don't know if she managed to join us because she had an urgent issue and she left for some time. She told me that she will try to connect. And then Marco, João, and Constantine for the roundtable. And I also would like to call two other persons. Professor Jean Toughness, Jean, you are somewhere here, right? I would like to call you to this discussion. Jean Toughness, you are here? No. And Dr. Amaya Iguarda is Dr. Amaya.
Yes, I'm here.
Okay, thank you very much. Let me see if I find Jean Toughness. I was told to invite him for this round table. Maybe he's not around. Okay. No problem. He will join us. So thank you, Amaya. So for this discussion, Amaya, since you were not a speaker, I would like to invite you to take the word to kick off this discussion, this roundtable, and maybe you have some comments or questions or some discussion you'd like to start with our speakers.
Thank you very much for giving me this opportunity. I am Amaya Gartua. I am co-secretary of the Human Materials Platform and the Alliance for Materials. It is a congratulations for the organization of the event. Giving me this opportunity, I think that we have a very big challenge for designing the futures safe by design and sustainable by design materials. Then within the European Commission, there is an initiative in terms of trying to design the criteria related with sustainable by design to design at the face of the concept of the material building the product, and also considering the process during all the life of the production chain. Then for that, it's necessary to involve all the stakeholders related with the sustainable chain. And then it is necessary to monitor the life cycle assessment, the footprint, but at the design phase. Then I have the vision that for those components that are moving, then for example, tribology could be a good way to design materials at the early phase of when you are designing a component. And also to try to highlight what is the consumption of energy. And we don't have the carbon footprint of each material, each process, each product. And we have to build this in the future. Then I will bring to all the stakeholders to give the opinion about that. And also I open the session for also other aims or other needs that it may have during that has been raised this time. I put the concept that has been highlighted today when you bring materials and bring electronics together, then it is not just a material, it's more than a material, it's an intelligent materials, but what to do it during the recycling, all the life, how to separate this and how to handle this. I think that we have the breakthrough to the future in order to make a sustainable design, sustainable solution for the society of today.
Thank you, Amaya. Does someone, some of our speakers would like to make a comment or to follow up on the comments raised by Amaya?
Of course, we follow up, but in some sense, and when listening Fuzzy and also Professor Galiotis, in some way, there appears the doubt that advanced materials or composites that have more and more functionalities and driving that incredible properties, but if in some way are we not overestimating the possibilities of recycling of it? Just a question that if they feel that probably the levels of recycling that we have as a goals when you see how different are the materials, how if we are not overestimating the possibilities on the percentage to do that, just a perception, maybe wrong.
Yeah. Can I speak, Fatima? Can I react to that? Okay. No, I agree with you. I think it's a bit of a question, because the way we traditionally develop materials, we just look, when we have projects, just look at, okay, what is the goal? What is the functionality that I want? Then you start to develop the materials based on that target. Now, now that we have this whole recycling and sustainability issues, it needs to be incorporated in the very early stages, even in the conceptualization of the idea in the beginning. And that starts to be difficult, right? Because you shrink a bit all the possibilities that are over there to achieve the performance. But I recall that already, I mean, when I was at Tata Steel, already we were incorporating that early in projects, but it's quite difficult. But if we want to start to have materials that are recyclable, we need to, that's for me the path to start to do it that way, because doing the whole development, putting all the investments, developing a solution, and at the end thinking, okay, how am I going to recycle it? That's the traditional way of basically developing materials that will not work. Soon we see that, we see the problems that are all linked to it. So that means that we need to influence, or let's say those who are giving the money for R&D projects, funding for innovations, and also even the private sector, they need to take that into account from day one. That's how I see it.
I think I agree with this, with what Fuze is saying. And I mentioned this example of the symmetry of airplanes. I think if you haven't seen that, I think just Google it. And it blows your mind. There are kilometers of airplanes that out of service. They never thought, okay, and we're talking about metallic structures. They never thought, what is going to happen at the end of a life cycle of an airplane? I mean, how many deserts can we have to fill up with these structures? So I think we're now at a very critical historic moment where whatever we do, we should inbuild the recyclability. It's a concept. It has to come in. Even for the wind blades, they never thought. Take the wind blades. They are monstrous structures made out of thermosets. What do you do with this? I mean, they shouldn't have been like this. Why not thermoplastics? Okay, you may say, oh, they may be creeping a little bit. But for a wind blade, it doesn't matter. You're not flying on a wind blade. If it's a bit of creep, of course, the fiber there will resist creeping. So with the thermoplastic, you can take them down. And okay, it's costly. You have to then reshape it so they can use it again for something else. But at least it is a solution rather than taking the wind blade and leave it on your doorstep as to rot. We've done a lot of mistakes in materials, and not just materials, structural development in particular. We're using materials, advanced materials, and now I think we have to pay the price. But now, from now on, the political will is for recyclability, for materials that have structures that have to be deassembled and rebuilt in a way. And that, of course, it will be an added cost to the material and the structure development. It cannot be just free of charge. But the other possibility of rotting away huge structures on different places of the planet is not, it's something which has to be stopped.
Yeah.
So, and I think it's we're at the beginning of the road, in a way, particularly for lightweight material, because lightweight seems that you can make huge structures. At the same time, you have to be able to deassemble and recycle.
Fatima, can I say something?
Yes, sure, João. Okay. Go ahead.
Well, when we are developing a new material, we have first to decide if we want to decide to make a composite for a structural application or for a non-structural application. And if it's for a structural application, if we try to do it with a thermoplastic, it will be, of course, very hard work to do, and the success is very doubtful. So we use thermosets for wind blades and for other structural applications because it has been proved that when we try to do it with thermoplastics, it does not work. It's only this is the question.
Okay, it doesn't work, but now with adding nanoparticles to the matrix, the thermoplastic, we've seen an improvement of the thermoplastic properties. That was my whole point.
Professor Galiotis, we had the project with a colleague of you, which also Costas. It's Costas Kiparisides, you probably know, yeah?
Okay.
And we have proved in this project that when we use nanoparticles and we try to do nanocomposites on the resin, the rheology of the resin is such that it will not impregnate the fibers properly.
Yeah.
The problem is that when you put particles with specific area inside the resin, then the rheology of the resin is completely different, and it will not impregnate the fiber properly.
The MFI with the graphene is because graphene it doesn't really stick well to anything. So in fact, it is much better than any other nanomaterials like nanotubes or other nanoparticles. So here you have.
But when it does not stick well, it will not transfer momentum, because fibers, as you know, fibers and composites are based on transfer. If the adhesion is not there, it will not transfer.
We don't want them to do structural functions. I think you got this wrong. The fiber.
This is a very exciting discussion.
Yeah, the fiber would. The fiber will do the structural function. The nanoparticle is doing something else. So they may help the processing of the thermoplastic, and also it will be against creep and other properties, thermal properties, etc. etc. So anyway. This is a round table. A round table, we have to debate things.
Thank you very much for this great discussion. So coming back a bit to our main issue is that I would like to share some visions and some opinions how advancing materials can really boost the industry competitiveness, because there was a clear message from this discussion that novel industries, products with added value, novel products rely on very important developments of material levels. I think Fuzishi has pointed out a very important issue in the representation is the time to market. Fuzi, can you elaborate a bit more on what, according to your experience, how can we really, how long it will take to come from something very new till the moment we can see it in our daily lives in the form of a product?
That's a bit of a hard question. It really depends on the applications, right?
Yep.
So obviously, if you have safety concerns, if it's a structural part or not a structural part, so it will take much longer. If it's, as I mentioned in the presentation, you have different levels, different incremental development. When you change something on the surface, for example, you change your coatings and it's on existing system, then it may take 3 years. If it's a completely new material, like we have, for example, if you think of hydrogen cars, right? That's something completely different. Then of course you will have a long. It can take up to 20 years. So it depends on the application, it depends on the level of novelty. Then it can go from 3 years to 20 years. And along the way, whether you have, if you get the investments, if you get people putting the money or not, for these technologies to be able to grow and get a bit of the scale up. So this is where the policies play a big role, right? So if there is a policy that tells that you need to have batteries made 90% made of recycled material, you can be sure that everybody is going to put all the efforts to get that happening, right? Because there is a policy, or if there is a strong market drive, then for sure it will happen. But that means that then money will go into those areas. So it's a bit of a, it's not a clear answer with a clear number. It depends on the applications. But
please go ahead.
And
sorry, go ahead. There was a gap. Sorry.
Maya. So I'm passing you the word to Maya.
Hello. One of the issues that I think that it could facilitate all the processes to have the track of CO2 footprint in each step of the process in terms of analyzing in order to minimize the environmental impact, and also try to track the materials, because if you at the end of the life knows which is inside the material, then it will be possible to recycle. Try to do things in a way with a protocol that you can track the evolution of and transformation of the material at the end of the life. And it could be a protocol in terms of that everybody thinks about in the same way in order to implement a sustainable materials concept from the design phase, but that could, at the end of the life, could be in one way known what the material is and how this could be the end of the life. And if this protocol could be follow up in a general view, I think that we could enhance the sustainability of the process, of course, with the development of all the process related with recycling and added value of reuse, increase the life. The increase of the life is one of the things that could benefit the most the sustainability.
Okay, thank you very much, but I'm afraid we are running out of time. So this was a really very nice discussion. It's a pity that we don't have more time for it, but I'm sure that there will be a lot of exchanges of messages and viewpoints to better clarify some of the pending issues from this discussion. I would like now to pass the word to Dr. Renzo Tomellini. I think he is here.
Yes, I'm here.
I'm sorry. And Professor Tomellini is the head of the Technical Secretariat of the Italian Minister of Ecological Transition. So I kindly invite him for the wrap-up of this session and to share with us your viewpoints, your comments, your feelings. Thank you very much for accepting our invitation and be here today with us.
Thank you for inviting me. For me, it was a joy to see micrographs, to see scientific data and listen about the progress.
Renzo, can I add something about you, Renzo?
You are the boss.
I have to say that is a special moment for me because I'm a great friend of Renzo for years and years. He was responsible for generating the common house that EUMAT is taking profit of it. And moreover, he is a very enthusiastic guy for science. And thank you very much for all the support that you gave at the European community dealing with materials. The floor is yours.
Thank you, Rodrigo. The common house, how many things, and the nanotechnology strategy, and my last work at the Commission, the editing of the Horizon Europe that has been approved in the 12th of May for 95.5 billion. So, now interesting, I have been borrowed now to the Italian administration. I'm seconded by the Commission, and I'm now in Roma, where I'm the head of the technical secretary of the Minister for Ecological Transition. Will be the time of the government, so will be not an infinite time, but for the moment I'm here helping for the National Plan for Resilience and Recovery. Thank you for the invitation. I was very happy, really happy to see you, Rodrigo, and the colleagues, and Professor Galiotis, and all the colleagues I know since years. Science, material science, we know very well. Started with Paleolithic, from Paleolithic to Neolithic, and now to Anthropocene. We know a lot. We don't know everything. Now the question is, do we know enough? And surprising and incredible to say is, no, we don't know, still don't know enough for coping with the new challenges. So the struggle for the generation of new knowledge in material science must continue. And very happy, I was mentioning just a moment ago, Horizon Europe will provide an important frame of collaboration, cooperation, and financing for material research. I was listening the classical debate about structural materials, functional materials, biomaterials. This is for the pleasure of the speculation of the analysis. All the materials are purpose-driven. So you had a session on digital materials, the active materials, or better reactive materials. Materials are purpose-driven. Some years ago, we were using the term of materials by design. And so thinking or rethinking about materials. And of course, it was also mentioned the economic issue, the trade-off with the cost and the economy in the process, and the raw materials, because the point of the raw materials is something that in the strategic point of view has to be considered in terms of security of supply, in terms of diversification of supply, in terms of substitution of the raw materials when needed. Now materials have a special mission. And this is my job now, and this is the argument I wanted just to touch in very rapidly. The special mission is called CO2. It's called decarbonization of the process. It's called then also the sustainability of the material. Nobody proposes to have a CO2 tagging on the materials. It's not something that is in discussion, but yes, the decarbonization, the CO2 is the special mission for the materials now. For the postdocs, we already witness an historical phenomenon that is framing the production and delivery of products, which is the extension of the responsibility of the products for the producer up to the end of life. So more and more the product is thought in a longer cycle approach. So we start with the eco-design, the collectability, the dismantling, the reuse, the recycling. So, and all these cost energy, cost CO2. And this is with the purpose of keeping the embedded energy that every product has, and also the knowledge content, the function, the added value that the product has. The same for the material. We don't want to generate extra CO2 in this, because now you know very well the target, ultimate target for all of us is to have a net zero CO2 emission in 2050. Net CO2 emission, of course, but this means for all of us an extra engagement. And for this, is the point that I was mentioning just at the beginning. Incredibly to say, we don't know enough. We do not know enough about the materials. We don't have all the knowledge that we have. Products, but also materials have even new business models. For the product, we know very well. For the reagents in our laboratories, by origin, I was a chemist, and we know well that we go from buying the product, the reagent, the material, to the function. We buy the function of the item that we consider. So also the business models are being innovated. I was listening with pleasure the concept of nanostructuring and nano addition trump elements in the materials. We know well that whenever we add some new elements, this can be costly in terms of the moment of the dismantling or of the recycling. For instance, if we add alloys in steel, when we have to recycle these, and we know the steel is theoretically recycled infinite times, but then in the secondary metallurgy, we have to introduce some extra treatment. And of course, as usual, cost, as usual, CO2, as usual, energy added to this. So I didn't want to make it long. It was just a point of celebrating the pleasure of being material scientist. You are material scientist, I have been. So materials are our past, our present, but our future. And this special mission, sustainability, this special mission CO2 is really something new for the materials that will influence our way of thinking in the coming decades, up to the ultimate target that we have of decarbonization and the intermediate targets that I don't list, otherwise I would be just boring. Rodrigo, I'm sure, expects that I end with the classical phrase that we like to repeat each other, simulating some cinema and television spots. I was talking about a special mission, but the classical phrase that we tell to each other is that without materials, it's impossible to do anything. And as we like to say, no materials, no party. So thank you, Rodrigo. Thank you, friends, for this, and congratulations for your work.
Thank you very much. Indeed, no materials, no party. Yes. But we want to have the party of life and the part of the future. Thank you very much. So I think that now it's time to go. Can I give the floor to Rogério, please?
Yes, I think we can move now to the closing session. Who is the first speaker in the closing session? Is it Rogério?
Yeah, it's me. Sorry. Hello, Fatima. Thank you, Fatima. Thank you, Rodrigo, for speaking with the microphone mute. I just will start only by saying just a couple of words, just by saying that this event was something extraordinary. Not longer than 1 month, the organizers were able to make this conference, gathering the top key decisors in material science and engineering in Europe, gathering this today to exchange experiences, visions in what we can do in our scientific area. During all this day, we have as a baseline more than 100 people assisting to this meeting. The meeting was recorded. I think that in some time, a couple of days or a couple of weeks, maybe we can, and I would like to do so. It is a challenge to the organizers, but I think that we can disclose a written summary of the conclusions and of the topics which were spoken by all the participants during this day. And so these are, I hope that we can make with some periodicity once each year some type of event like this one, gathering people and worldwide quality and expertise in material science and engineering. And at the end of this day, I'm very happy, not only as a scientist in material science and engineering for the last 3 decades, but also as president of science and engineering school, a large one here in Portugal. I think this is the way that science, technology has to walk from now on, to gather people, to join people, to exchange ideas, and to walk in a certain direction, with a certain vision, with some dreams, looking for a better future. So I'm very happy at the end of this day, and thank you to you all.
I would like just to add that to thanks that we have got 298 people registered, that all the summary that Rogério spoke, we will arrive to them, the conclusions. Thank you very much.